In the in the last video, we did a DFT example and we talked about some properties. Now let's build a bit of intuition. So again, I use my brain and I kind of drew this beforehand so you wouldn't have to sit here and watch me draw it. But we have two square pulses here. Big N is 256 for each of them. That's not important here. It just means we're sampling 256 times. What's important is the pulse width. So here we have a pulse width of 12 and here we have a pulse width of 6. So my question to y'all is, what do you think the DFT of both of these signals will look like? And I don't mean like draw it from scratch. I mean like intuitively, right? Like let's review this, that the DFT is going to be, I'll do it in blue. The DFT is going to tell us, hey, for this given frequency K, a frequency of 3, how much do you contribute to this signal? So you might be this much. Okay, so what I'm trying to get at here is I want like high and low, as in one of these things is higher frequency than the other. And take a second to pause and maybe think about which one of these would you say is of a higher frequency. And my answer would be this one. The reason why is because what is frequency? Like high frequency means going up and down faster. There's high frequency, this is low frequency. They both go up and down, but this one does it quicker, correct? In a given time range, it will do it more times than this guy in a given time range. So which one is going up and down faster? Well, I would say this one, right? Because they both start off flat, but this one has a longer time to wait before it goes down, and this one has to go down quicker. So this one, I would say, is higher frequency, right? And this one is lower frequency. Okay, and there's an important point that I'm about to make here, which is that me saying this is higher frequency doesn't just mean it's going to have one spike up here. I mean that, okay, obviously this wave, this whatever this square pulse is, cannot be represented with one frequency, right? It's going to be represented with a combination of frequencies. But what I'm saying is, on average, those frequencies are going to be higher here than they are going to be here, just because this signal by nature is of a little bit higher frequency. It's changing a bit quicker. So what I'll actually draw the DFT now. Again, we're going to use our brains here and say, look, I could plot the DFT 0 to 256, but that's annoying because for a few reasons. Actually for one reason, which is that my DFT is symmetric. So why would I plot my whole DFT and then just copy it on this side? Instead, what I'll do is I'll plot it from negative 128 to 128, correct? Because we know DFT is periodic every n, so that's every 256. So this captures a full 256 DFT sample, so we're good. And then this will be symmetric. So I really only need to calculate the DFT here, and then it'll just go to the other side. Okay, so it'll flip across, because we know for real signals the DFT is symmetric. Very important property. So this is what the DFT looks like for this guy. Boom, 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 boom. Okay, and this is what the DFT looks like for this guy. Boom, 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 boom. That should be symmetric, but let me draw it a little bit better. Oh, it's because my 128 and go. Okay, never mind. It's because I drew this freaking 128 so far away. Oh my gosh. Like if 128 is here, then my DFT is going to look like this. And I'm telling you this, by the way. This is not like something you would be expected to know, but you should be expected to reason with this, right? You're saying, okay, here, a high frequency component, I have a good amount of it. Here, I have less of it, right? Here, this frequency, I have none of it. So whatever this frequency was is a pretty high frequency. In this signal, I have a lot of it. Here, I have none of it. So clearly, these bars, right, are when the frequency is high, like, yeah, we're getting some signal here, right? Here, when the frequency is high, now we're not getting much, right? So this is why this Fourier representation in K is of lower frequency than this one. So this you should just be able to reason with yourself, say, hey, the one sentence reasoning is, look, this pulse changes quicker than this pulse. So this pulse should be made of higher frequencies, and we can see that when we take the DFT. That's it. Okay, now let's find DFTs of more important functions. This is like crucial because we're going to find DFTs of very important functions that will come up in a lot of proofs and you'll be tested on in exams. Let's first find the DFT of a delta function. Okay, so we're looking to find the DFT of the function delta of n, which, to remind you, hopefully at this point this should be very much review. It's 1 if n is 0 and then 0 else. Okay, so what that looks like, hopefully again this should also be review in the n domain, time domain, at 0, 1, 2, all the way down to big N minus 1, we've got a pulse here. So here's our delta function, then zeros everywhere else. Okay, we're looking to find its DFT. Okay, this is not as intuitive. This is one of those problems where I say do the math out, get the answer for the DFT, and then explain it to yourself with intuition. Because remember, like, if I have a signal that looks like this, right? The DFT, if the delta function looks like random spike and then everything else is 0. Like, what frequencies make this up? That's not entirely clear. Okay, it's not very obvious. Okay, let's instead of trying to think about it intuitively, let's actually just literally plug and chug into the definition of the DFT. Remember, the general definition of the DFT is big X of k is 1 over root n, sum from little n equals 0 to big N minus 1 of our signal in time. So this is little x, this is big X, times e to the minus j 2 pi k n over n. So what I'm going to do is I'm going to replace our xn with the actual signal we're looking at, which is delta of n. So this signal that I actually care about is delta of n. Okay. Very good, very good. Okay, now this looks like a really messy sum. What do? I have to evaluate the whole sum, but you realize that we're summing from n equals 0, so we plug in 0 in, great. After that, once we start plugging in 1 and beyond, this term will always be 0, right? Because delta is defined that way. So what this really means is I only really have to consider when little n equals 0. In this whole sum, I only care about one time, and that's when little n equals 0, correct? And so when little n equals 0, what happens? Well, then I get 1 over root n. I only consider when little n equals 0, so I get delta of 0 times e to the minus j 2 pi k times 0 over n. And so what does this become? We remove the sum. That logic should make sense because we only care about, of all these, n equals 0, then we go n equals 1. Anything onwards we don't care about because that'll make this thing 0. So this becomes 1 over root n. The delta function evaluated at 0 is exactly 1. And then e to the minus blah, 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 0 up here means this whole thing is 0, so this just becomes 1 as well. So if you notice, our answer becomes 1 over root n times 1, which is just 1 over root n. Okay, now this is a little bit confusing because, again, 1 over root n, this is not going to look like a square root function when we plot it. This says that x of k is 1 over root n. So the way, again, you have to think about it like this. You have to think about, okay, when I go now to the frequency domain and I'm plotting my DFT. Oh my gosh. Okay, plotting my DFT. I'm plotting it against k. So I need to figure out, okay, what is x of 0 going to be? What is big X of 1 going to be? What is big X of 2, etc., etc. So big X of 0, that's going to be 1 over root n. Big X of 1, there's no k in here, right? So it's going to be 1 over root n. So what you realize is that in the frequency domain, this is actually just a bunch of constants. So the DFT is a constant, which means we're saying each frequency contributes an equal amount. It's kind of a surprising result. It's not that intuitive. Right? It's saying that if you were to somehow take all the frequencies and combine them up, giving each one the same weight, you would be able to, they would basically cancel out everywhere else except for 0. And at 0, you would see a nice pulse, and then everywhere else you would see everything else would cancel out, which is kind of actually like pretty neat if you think about it. But what we figured out is that the DFT of so what we figured out is DFT of delta is a constant. right? 1 over root n is a constant. N, big N, has been figured out from the beginning. We know what big N is from the moment we sample our signal in the first place. So it's a constant, okay? So one other also interesting thing to note here is that if you were to calculate the energy of this signal here, so how do you calculate energy? You use the formula, right? The energy of our signal in time is going to be the sum from n equals 0 to n minus 1 of x times its conjugate, right? You do the inner product with itself, and that's your energy. And if you do that here, find the energy of big X squared, what you will notice is that in this case here, the energy of our original signal in time, so I'll do, here, let me make this clear. For energies, you can notice that the energy of our signal in time is equal to 1, and so is the energy of our signal in frequency. Okay, and this might be say, hey, this might be lucky, but is it a coincidence, or is it a pattern that going from the time domain to the frequency domain preserves energy? And that's actually not a coincidence. That's a very important property. We'll prove it in a later video. But this is called Parseval's theorem. Parseval's theorem. It basically says that going from one domain to the other, time to frequency or vice versa, preserves energy, which is why we can be so reliant on these transforms to do analysis. Okay. Anyways, that's a little bit of a whatever. Like getting a little bit ahead of ourselves. Let's now find DFT of a shifted delta. Okay, and this is something, maybe these are like, I don't know, I think these are pretty like fun to just try and work through, like using the definition, see if you can plug in and get something nice out of this, because sometimes it gets a little bit ugly. But let's first define a shifted delta. So a shifted delta is a delta that's been moved over n naught units to the right. So this is going to be 1 if n equals n naught. So if the stuff inside is 0, 0 otherwise. Okay, so again, this looks like a delta, but it's been literally shifted to n naught. So this is n naught. This is where we see the spike. Everywhere else we see 0. Okay, I won't do a more intricate diagram than that. Okay, so let's do our why am I blanking on this? Let's find the DFT of this thing. So x of k is 1 over root n sum from n equals 0 to n minus 1 of my signal, which is delta of n minus n naught, times, let me write that delta clear, my signal times e to the minus j 2 pi k n over n. And I'm not going to lie, like, these are like kind of, they're kind of daunting to look at. Like, you look at this and you're like, there's no way this is ever going to simplify. Well, look at what we have. We have a delta function, right? Once you see a delta function inside a sum, your life gets so much easier, because this goes from n equals 0, n equals 1, n equals 2. We don't care about any of them. The only one we care about is where n equals n naught, because that's when this guy is going to evaluate 1. So we care about when n equals n naught. And so that allows us to simplify our sum to big X of k is 1 over root n. I only take the one where n equals n naught, so I have delta of n naught minus n naught times e to the minus j 2 pi k n naught over n. And this thing becomes delta of 0, which is exactly 1. So this is 1, so it goes away kind of. And then what do we end up as? We end up as 1 over root n times e to the minus j 2 pi k n naught over n. If you notice, this is also quite confusing. One side note here is that before we defined ekn as a function of n is e to the j 2 pi k n over n, right? This says, hey, I'm plugging in n's here as my inputs to the function, and I'm choosing k as a parameter. I can reverse this logic and say enn as a function of k is going to be the same exact thing, 2 pi k n over n. It's the same exact thing, but just what I'm doing is reversed. Here, I'm choosing n, I'm fixing n, and then I'm plugging in different values of k. Here, I'm choosing k and plugging in different values of n. So here, what I'm saying, all this is to say that I can take this guy and write it as 1 over root n e to the n naught n of k. Okay, so all this is another complex exponential with frequency n naught. Okay, so what this guy is it's exactly analogous to here, right? But instead of being as a function of n, it's being as a function of k, and the frequency here is n naught. Okay, so another way you could think about it is, look, you can put, like, having it as a function. If I have a function x of t that looks like this, right? And I have t here. And then I have a function x of alpha, but it's the same function x, and I have alpha t. This is going to look exactly the same, right? It doesn't matter what the variable I'm plotting it with is, right? So it doesn't matter whether it's k, whether it's n. This is still a complex exponential with frequency equal to n naught. What we figured out is that if you shift a delta over by n naught, then, let me make some room now. What we figured out is that if I take this guy and find its DFT, what am I going to get? I'm going to get some complex exponential with a given frequency n naught. So it's going to look like some, remember, complex exponential is technically a real part and an imaginary part. Oh shoot, this is something I didn't mention at all. Hold on a minute. This is very important in terms of interpreting the results. The DFT takes in a signal that's usually real and outputs something complex, right? Doing this outputs a complex number. In this scenario, it didn't. It outputted a constant. But in this scenario, look, our result is a complex number. So the question is, when you see all these graphs of the DFT, you're like, how the heck are they graphing this as if it was a real number, right? When I plotted DFTs, I plotted it just like, oh, at this point it's this much, at this point it's this much, and then you plot the whole DFT, right? But this only has the real part of it, right? So it's customary to, when we actually want to visualize the DFT, we focus on the magnitude. Okay, so the DFT itself might be some complex number. Well, what we do is we just take its magnitude and plot that. So instead of, worrying about cosine theta plus I sine theta, we literally take the magnitude of this whole number and that gives you out a real number always, and that's how we interpret the DFT. Okay, so that's more of just like a understanding that tripped me up for a bit. I was always like, hold on, this DFT is this e to the e n naught n is cosine plus I sine. That's an imaginary number. That's a complex number, right? How the hell am I viewing it like this? The reason why is because if you take the magnitude of this guy and plot it, it just looks like a sinusoid. Okay, I think this video is getting quite long. Let's keep going because there's kind of a point here. So what we figured out so far is that DFT of a delta is a bunch of constants. We figured out that DFT of a shifted delta, DFT of a delta is just a constant function, right? DFT of a shifted delta is a complex exponential with frequency n naught. Okay, now let's find one more. Let's find DFT of a complex exponential. So what we figured out so far, let's figure out what we have. We have our original time function, and then we have its version in the frequency domain. So we realize that, okay, if I have a delta in time, that's going to be a constant in frequency. If I have a shifted delta in time, that's going to be a complex exponential in frequency. So now let's see what happens. What if I have a complex exponential in time? Let's see what the frequency relationship, what the frequency representation of that is. I.e., right, to go from here to here, we took the DFT. Let's see what the DFT of a complex exponential is. So again, let's do this quickly because I don't want to spend a lot of time. So let's write our complex exponential. X of n in the time domain is e to the k naught n of n. So I'm taking my signal to be a complex exponential with frequency k naught. So this thing is equal to 1 over n e to the j 2 pi k naught n over n. Okay, great. Let's use, instead of using the whole sum definition, let's use this definition, which is the frequency, the DFT of my signal is big X, which is also interpret it. I wrote it incorrectly in previous videos. I had actually written it as 1 over root n times the inner product, but the way the inner product works, it actually cancels out this 1 over root n. So the DFT is actually literally just the inner product of EKN and EK naught n. Okay, so remember the DFT, just like we can write it as that whole n equals 0 to n minus 1 of x of n, e to the j, blah, blah, blah. If we rewrite e to the j as its conjugate, right, as e minus k, as e kn conjugate, then we can interpret this whole DFT operation as just an inner product between x of n, our signal, and a complex exponential of frequency k, right? In this case, our frequency is k naught because that's what we've plugged in, right? That's our signal, e k naught n, and then we're inner producting it with all the different possible values of k. So if this doesn't make sense, just go back to the video we wrote it as an inner product and then work through it that way. I don't want to spend too much time on it. If we write it like this, right, as an inner product, then we know that the inner product between two complex exponentials is going to be the delta function of their with the exponentials, right? Because we said that when k equals k naught, this thing's going to be 1. When they're the same, it's going to be 1. When they're different, it's going to always be 0, right? This is because complex exponentials are orthogonal, right? This goes back way back to discrete signals, right? But these things, if these numbers are different, then they're going to be 0. Their inner product is going to be 0. So notice, look what happens when we take the DFT of a complex exponential, we get a shifted delta. Okay, and for the sake of time, I wanted to do the example where we take the DFT of a constant and show that, okay, if you did take the DFT of a constant, you would get a delta. Okay, so clearly you can see that there's some pairs here, right? If you take the DFT of a delta, you get a constant. If you take the DFT of a constant, you get a delta. If you take the DFT of blah, you get this and this and that. They go back and forth, right? And you might think that there's a pattern going on there, and there is. We will talk about this in the next video, but this is kind of motivating. I'm trying to think, is there any... The idea here is that you have pairs of signals and their Fourier transforms, and those pairs remain the same. So like if you have a signal and you take its Fourier transform, its DFT, you take that thing, you take the DFT back, and you get the original signal again. There's a little bit of a nuance there, but we'll talk about that in the next video. The one thing we did talk about, though, is that whatever the energies are in the time domain, so whatever the energy of the delta function is, it will be equal to the energy of the constant function. The energy of this is equal to the energy of this, and so on and so forth. So we learned that the DFT preserves energy. Yeah, so sorry, this video was kind of all over the place. I think I touched on all of the important concepts. It was kind of in a jumble, so apologies for that. Hopefully the other videos are more structured. But yeah, see you in the next one. Sorry for the long video again. My bad.